Hello, and welcome to the next chapter, section 3.1. In this section, we're going to be learning rules of finding derivatives or shortcut rules so that we don't have to go through the limit of the difference quotient every time we want to find the derivative. So we're going to start with power functions. And if you remember, power functions are of the form like g of x here, ax to the n, where a and n are any real numbers. And a certain type of power function is a polynomial function. So polynomial functions, the sum of these power functions. So before we look at power and polynomial functions, we'll start with the constant function, because that actually sort of is a special case of a polynomial or power function. The constant function f of x equals c is just a horizontal line. So we know that the slope of that is 0. So we know that the derivative of that is 0. So that's our first quick shortcut rule. And notice that in this section we're using that operator for the differentiation operator here. The next function is the identity function, so that's just f of x equals x. You know that's a line through the origin with a slope of 1. So we know that the derivative of the identity function is 1. Multiples of the identity function, like 2x, 3x, etc. You know this has a slope of 2. That's a linear function with a slope of 2 through the origin. So that derivative is 2. This is a linear function with a slope of 3, etc. So any linear function has as its derivative its slope. So now let's look at the general power function where n's a positive integer, or that power is just a positive integer. So these are the things that make up polynomial functions. So let's differentiate x to the n. That's the most basic one. So we have the limit of the difference quotient. And let's look what happens when we expand that binomial x plus h to the n. So this is, if this were x plus h squared or x plus h cubed, you're going to have a longer and longer string of terms. And if you recall, that's using the binomial theorem. You don't worry if you don't remember the binomial theorem. Just know that the only one we're going to need to worry about is this one. We'll talk about that. So notice that when we expand that numerator, those x to the n terms cancel. And then we're going to cancel common factors of h from the numerator and denominator. And only this term is going to be left. So that h will be gone. That would be canceled with the denominator. All these other, once we take the limit as h goes to 0, all these other terms are going to go to 0 as well. So all we're going to be left with is this second term that shows up in the numerator. So all these other terms go to 0, so we can say that the derivative of x to the n is this constant c sub n minus 1 times x to the n minus 1. That's the term that was left when I took the limit. So the only coefficient we care about is that c sub n minus 1. And if you remember the binomial theorem, and even if you don't, it's really not that significant. That c sub n minus 1 is just n itself. So bottom line, it boils down to the derivative of x to the n is n times x to the n minus 1 power. So you can remember in your head as you bring down the exponent and then subtract 1 from it. Here's the example of binomial expansion. And again, everybody else you don't care about except this one. So gratefully, you can put the binomial theorem aside and not have to think about it again. So let's just look at a couple of examples. So f of x equals x to the 9th. My n is 9. I bring down my m, 9, and then subtract 1 from the exponent. The derivative is 9x to the 8th. Same thing here. Now let's look at another example, or another power function, but this time let's let that power be negative as well. So a negative integer. So let's say d dx of x to the minus 3rd power. Well, again, deriving it from the limit definition, we have our difference quotient. Here we have found a common denominator. I multiplied that h by the denominator. We expand it. Notice that the x cubes canceled, and all that we're left with, once we take that limit as h goes to 0 here, all we're going to be left with is just minus 3x squared in the numerator. So once we take that limit as h goes to 0 in the numerator and denominator, I'm left with minus 3 over x to the 4th once I cancel factors of x. So if we rewrite this with a negative exponent, that's minus 3x to the minus 4th. So actually the same process applies. Bring down the exponent and subtract 1 from it. So actually this applies with any power, not just integers. So any real number in the exponent we can use this shortcut rule on. For instance, s of p equals the square root of p. So when you see radicals, you're going to want to rewrite those as fractional exponents. So this is p to the 1/2. And now we can apply that power rule. So bring down the 1/2, subtract 1 from the power, and I get 1/2 p to the minus 1/2. And that's how we write it, getting rid of the negative exponent.